Thank you for the introduction, Martha. I'm reminded of the Monty Python line, now for something completely different. These solar cells are almost every aspect of them is different from the last speaker's solar cells. They do convert sunlight to electricity, but other than that, we're talking about single crystal materials now with very high mobilities, where it's very easy to separate the electron and hole from each other. And so you're focusing then on minority carrier transport in lightly doped materials. Anyway, the title of my talk is Light Management in Single-Junction 3.5 Solar Cells. Alta Devices, as Martha said, is a company that was founded to commercialize a single-junction gallium arsenide technology without concentration. And I hope in this talk to convince you that the optical side of the solar cell problem in these highly efficient, highly luminescent materials has been undervalued traditionally in this community, in the solar cell community, and that there's a lot of room for people from the LED community, for example, to get involved and think of the problem as an optical problem. There are many people who contributed to this work. I've listed below just the direct contributors to the work that I'll talk about today. So again, I'm going to be talking about a single crystal, single junction gallium arsenide device in a thin film, where the thin film is made by metal organic chemical vapor deposition, and then the film is lifted off, leaving a reusable wafer underneath it, and the film thickness is then controlled by the MOCVD growth. With this approach, we've managed to achieve record efficiency by the fact that we can access the backside of the device and precisely control the device thickness. And by having access to the rear surface of the device, we can do a lot of engineering to the reflectivity of that interface and how we manage the light within this thin device. If we think about the diagram that Gary showed about the steps within current collection in a conventional device, it showed, interestingly, the carrier separation at the junction and then carrier transport to the contacts. I'm going to show you there's kind of an implicit step that was missed in that diagram, that during that process of carrier transport, there are many ways the carriers can recombine. And depending on the mechanism of the recombination and what you do to engineer around it, that recombination need not be a fundamental loss in terms of efficiency. The optimal performance requires careful consideration of this recombination process, which produces recycled photons. And I'll go to that more in detail during the talk. And I hope to convince you by the end of the talk that high external fluorescence yield, that's the emission of light from the solar cell itself at open circuit, in this kind of device is an indicator of high voltage within the cell from high carrier concentration. So most of this talk is going to be from a pretty high level. I'm going to show conceptually how we think about it without going into the detail. Hopefully I can bring you along all the way to the end without losing too much of the audience that way. Shown here is a cartoon of a thick 3.5 solar cell. Traditionally in this community, 3.5 cells are grown on thick gallium arsenide or germanium wafers, and there's no particular attention paid to the absolute thickness except as far as yield and wafer breakage and things like this. There's no particular attention paid to the reflectivity of this contact. So even if the devices themselves are thick, the overall structure optically is even if the device itself is thin, only a few microns, the overall structure is very thick. And because the refractive index is basically matched throughout, the optical structure is very thick. If we consider a very simple model of absorption in a semiconductor from one pass of light, we get something like this as a curve of unabsorbed light as a function of depth. So we get exponential decay of the wavelengths with energy higher than the band gap energy. And as they're absorbed, they're generating electron-hole pairs that are hopefully collected by diffusion and then crossing the p-n junction to create current in an external circuit. Now, using a very simple optical model that just considers a slab of semiconductor material, which has some reflection at the interfaces, some loss mechanism within the cell, we can then think about JSC, the short circuit current density, as a function of the thickness of the cell. So as you'd expect, it's roughly exponential up to a point where you become somewhat limited by carrier transport due to loss mechanisms. The point of this slide is that to achieve industry standard values close to 30 milliamps per square centimeter for gallium arsenide, you really need close to 10 microns, or maybe that's an exaggeration, but at least many microns of material to achieve these kind of JSCs. And just to calibrate ourselves, the previous records before Alta's results were set by a couple of groups from Europe and Fraunhofer Institute and Radboud University. I don't know the precise thickness of these devices, but the JSCs were 29.6, 29.8. So these are kind of world-class JSCs for a single-junction gallium arsenide cell. I'm going to look a little bit more in detail at the loss mechanisms within such a structure. Throughout this talk, I'm going to use either this multicolored arrow or this green arrow to represent the incident light from the sun. And I want to make the point, the sunlight is a very broad spectral source, and that's the primary reason that we're at 28.8 and not some higher efficiency. It's difficult to efficiently capture across such a broad spectrum. So for the light that you do absorb, generate electron-hole pairs. These can be either collected by the p-n junction and generate current in the circuit, or they may recombine either radiatively or non-radiatively. For the materials we work with, single crystal gallium arsenide, the internal fluorescence yield is very high, 98 or 99%. That means of all of these recombination events, 1 in 50 or 1 in 100 is non-radiative. The vast majority are radiative recombination events, which means a band-edge photon is emitted during this recombination. And this is a very different kind of photon from the incident light. This is an old PL spectrum from one of our devices from a couple of years ago. The point I'm trying to make is that its width is something like plus or minus 20 nanometers, as opposed to the solar spectrum, which was very broad. So it's really defined by the band edge energy and wavelength. So I've drawn these in red to represent the effective red shifting of the energy. So you have all of these band edge photons rattling around inside this device. Some of them will be reflected. Another point I want to make is the angle is randomized by this process. So we have mostly normal photons coming in from the sun, and then this random distribution of band edge photons. So half of them are basically going deep into the optical structure, this thick semiconductor. The other half are hitting the top surface. A small fraction are within the escape cone of the top interface and are able to escape from the device. So even on an on-wafer device, you are going to see some emission. And you can use these as a kind of LED if you do electroluminescence on the cell. So using the same model to look at VOC and efficiency in such a device with a thick crystal substrate and no reflector. Even theoretically, the VOCs are limited to less than 1.07, and the efficiencies around 27%. And in terms of practically achievable, using these same groups' data, real efficiencies are below 1.05, real VOCs, below 1.05, and efficiencies in the mid 26% range, 26.4 from Fraunhofer. The cell I'm going to tell you about today has a VOC of 1.12, so it's a significant leap from these data points, and the efficiency 28.8 is higher than we believe is achievable without a thin film with a reflector. So if we talk about a thin film now, where the thickness is a few microns or less, with a very optimized, well-optimized reflector at the back interface, the first thing we gain is what we call light trapping. That is better capture of the incident photons from the sun. So again, using these green photons to represent light from the sun, most of it's coming in normal and reflected normal off the back surface. So straight away we get two passes effectively through the material. Again, I draw unabsorbed light as a function of depth into the cell. And with the reflector shown in green, the dashed green line, we can make the cell not quite twice as thin, but significantly thinner than you'd need to make a cell without the reflector on the back. We then lose some light. When you make the cell too thin, you start to lose light out the front side of the cell. The cell red light that didn't get absorbed even with two passes. You straight away can improve the performance by the fact that you have reduced the amount of semiconductor material in the cell. So the non-radiative recombination rate is reduced simply by that fact. But there's an additional mechanism going on that I want to talk about. So first, looking at short circuit current densities as a function of thickness. This can be significantly boosted for these thin, relatively thin cells. And you can start to talk about achieving these industry standard JSCs with a device that's less than 3 microns. There's another phenomenon that's going on that's actually more important in terms of the performance boost you get from this geometry, and that is what happens with the band edge photons, the recycled photons. We're now not wasting so many to the thick crystal of the cell, and if the semiconductor material is of significantly high quality and the reflector is of sufficiently high quality, you can have very efficient recycling of these photons. That means a recombination event in this device doesn't have to be seen as a loss anymore, because you'll have the recombination event, a photon is generated, that photon is absorbed. The carriers may or may not make it to the junction. If they don't, then they recombine and emit another photon. That has the effect of increasing the effective lifetime of carriers. You have a much better chance, A, of collecting those carriers, so that's it, a JSC boost, but you also increase the carrier density within the cell, so it affects the voltage of the cell. In these materials, because they're limited by radiative recombination, the lifetime is essentially set by the doping level for a gallium arsenide cell. For dopings around the 10 to the 17 mark, you get bulk lifetimes around 50 nanoseconds. But if you have very efficient photon recycling, this can be higher by a factor of 10 or more, because the lifetime is now extended by this photon recycling. One byproduct of that is that at open circuit, you have 10 times as many chances of the band edge emission escaping from the cell. So you have increased external fluorescence. So high-quality 3.5 materials are extremely efficient radiators of light, and if you design them as an optical device, you can get extremely efficient outcoupling of the band edge emission. This increase in the carrier density and the external fluorescence of the cell is seen in the modeling as a huge boost in the VOC. Remember, we were talking about VOCs below 1.05 in practice, where we've demonstrated 1.12. So that's a, I guess, 80 millivolt boost on previous records. One point I want to make I'll make the point later, but this points to the fact that the reflector is not just influencing the performance in the light, but curiously the dark current. But I'll get to that a little later. Because of this boost in the VOC, you get a couple of % jump in the efficiency that's possible. So that's all nice to talk about. How would you show something like that in an experiment? We fabricate our devices both in our baseline process as well as our research process by MOCVD growth of an epitaxial stack with an aluminum arsenide release layer. We can then, it's grown sunny side down, so what later becomes the front of the device is grown first. That gives us access to the back side of the device to engineer the optical properties of that reflector. It's bonded to a plastic substrate, so the final device is flexible. This is then submerged in hot hydrofluoric acid, which dissolves the aluminum arsenide layer. And if we invert the structure, we end up with this thin film on the reflector on plastic, and the wafer is left largely undamaged, available to be reused. The cell fabrication is then very conventional. We're restricted in temperature by the plastic, obviously, but we then do our cell fabrication on a thin film, on thin flexible film. As I mentioned at the beginning of the talk, this epitaxial lift-off process is very important. Originally we thought as a cost-saving mechanism only. We've since learned that it's very important from a device physics point of view. That we believe we have performance that would be impossible if we still had the device on the wafer, because we have access to the thickness of the device, the rear surface of the device, and the overall optical properties of the device. And that opens up a huge new world of design opportunities when you start to think of it as an optical as well as an electronic device. We need to maximize the performance of these band-edge photons in particular. Make sure we don't lose them either within the absorber or at the back surface reflector. With this, we're able to achieve 28.8% efficiency certified by NREL. This cell has a VOC 1.122. We have achieved 1.126 in a different device. And I believe this is the first gallium arsenide device with operating voltage above 1 volt. The JSE and fill factor, on the other hand, are very comparable to other groups within the industry. So even thinning the absorber with the reflector, we're able to maintain the JSE. So I want to dive a little deeper into the voltage side. This is the light and dark IV characteristics of the solar cell. The light IV is shown in blue, the dark IV is the dashed red curve. So I wanted to pick up the point that I touched on earlier, that you're actually affecting the properties of the cell in the dark also. The cell more or less obeys superposition. We can add the JSC to the dark current and pretty much map out the light IV. So by boosting the VOC, that's coming as a product of reducing the dark current. So we believe we have achieved lower dark currents in this device than have been seen before with gallium arsenide. I think that's an important point, that you're really changing the way the structure communicates optically with its environment, whether it's in the light or in the dark. If you think about a detailed balance model, the cell has to emit a certain number of photons to be in equilibrium with its environment. And so the more efficient it is at emitting light, the lower the dark current can be. One measure of this idea is a quantity some people call W or delta W, the difference between band gap and VOC. This is a slide from Richard King's talk a couple of years ago at the European Conference on Photovoltaics. The y-axis is depending on the curve, either the VOC, the band gap, or the difference between the two. The x-axis is the band gap energy. So he's mapping as a function of technology class the difference between cell band gap and cell VOC. And that's a measure of dark current and a measure of absorber quality. The closer you can get the VOC to be equal to the band gap, the better the performance of the device, obviously. And a rule of thumb in this field is typically that if you're around 0.4, you're in pretty good shape as far as this quantity W. With this cell, actually the 1.126 VOC cell, achieved W values that are below 0.3 volts, which I believe are the lowest that have been demonstrated, and right near the theoretical limits, according to Richard King's graph. Another couple of authors have looked at this problem more recently. Martin Green put out a paper this year about external radiative efficiency. In our group, we call it external fluorescence yield, but they're synonyms. They mean what fraction of recombination events result in external emission from the cell. The other paper I want to cite is Owen Miller, Eli Jablanovic, and Sarah Kurtz have done some excellent work in this field as well. So what Martin Green did, he took the record results as reported last year and took the measured external quantum efficiency, the reported VOCs, and the band gaps of the materials, and calculated what the emission spectrum ought to look like. And if you can see on the graph, the shape of this is the gallium arsenide ISE is the Fraunhofer cell that I mentioned earlier. Gallium arsenide Alta is our previous record, 27.6. The shape of the curve is unchanged, but the magnitude is 20 times higher. So shown in the table, 22% external fluorescence yield versus 1%, 1.3% for the Fraunhofer device. So this, again, is another measure of the efficiency of external photon emission at open circuit. I can use the same methodology, assuming the external quantum efficiency is independent of the cell, and look at these different gallium arsenide solar cells. I can then graph external fluorescence yield as a function of VOC. And we believe with our latest results, we're getting above 40% external fluorescence yield, which even in the LED community is a respectable number. This is a point Eli Jablanovic and others like to make, that an optimized solar cell is also an excellent LED, and we find that to be true for our cells. As far as further performance enhancement then, another point I want to make about this is that the returns become somewhat diminishing. To get to above 50% external fluorescence yield, the change in voltage that's remaining is around no more than 30 millivolts, and probably less than that is achievable. To make significant improvements beyond 28.8, we need to look at the short circuit current density. If you look simply at the band gap of gallium arsenide, in a best case scenario, you might achieve beyond 33%, 33 milliamps per centimeter squared, rather. In our cell, there are various losses. Some are unavoidable, some may be avoidable. We have a shading loss due to the front metallization. Even at a one-sun device, you can't reduce this to zero. We have an anti-reflection coating that's not perfect. It's designed to maximize absorption in the useful part of the spectrum, but has some loss associated with it. Window absorber loss I used to describe the the fraction of the spectrum that's absorbed in the front window of the cell but not collected as current. So you have relatively high recombination rate at the front interface of the window of the cell. Transport loss is the non-radiative recombination in transporting carriers through the cell. It's relatively small in our cell, but it's certainly not negligible entirely. And imperfect light capture is what I call the photons that hit the back reflector and make it back out the front of the device without ever being absorbed. And because our cell is relatively thin, we are always trading off JSC versus VOC to achieve maximum efficiency this way. We've never achieved above 29.8 milliamps per square centimeter, and I haven't seen that reported either. But theoretically, above 30 ought to be achievable. I want to just run quickly through how you might think about reducing these losses, boosting JSC. Reflection and shading can be further optimized, but they're probably in the 1/10 of a milliamp kind of range. Front window losses, there's a lot to be gained there, but it's a huge research project. Surface passivation, higher bandgap window materials, more advanced thinking about how you make the front window. We believe transport losses and imperfect light capture are really the ones to aim for in the near term. And so we're talking about transport losses in getting across the thickness of the cell and loss of light capture because of light getting out of the front of the cell. So we've already heard a lot in this conference about ways to make better reflectors, either textured or with plasmonics or diffraction gratings at the backside of the cell. I'm not going to talk in any detail about this, but I think that's a very promising area to improve the performance, even of these very high efficiency cells. Often this field tends to look at cells that are extremely thin, like 1/10 of a micron. But I think there's room for a demonstration of performance improvement even in a few micron cell. We believe JSC boosts are possible. With that, I'll conclude. We've fabricated a 28.8% efficient gallium arsenide solar cell by optimizing the optical properties of the cell. We tend to think of our cell primarily as an optical device. The optimal design requires not only capturing and converting the incident photons, but making sure you don't lose the photons that are emitted within the cell. We use the epitaxial lift-off technique to achieve this. I'll be happy to take any questions. Thank you for your attention.